Hello, hello, hello. How's it going, everybody? Welcome to our CP164 midterm review session. I hope everybody has had a great reading week thus far. Hopefully, you're studying for exams well and not too stressed out about the CP164 midterm. And if you are, well, you've come to the right place. Hopefully, we take a little bit of the stress off of your shoulders. So, before we get started, anybody who's been in these review sessions before knows that we'd like to get everybody their Lorry experience record up to date. So I'll leave this up on the screen for everybody in the Twitch chat right now. People watching afterwards, just scan this QR code and sign up through the type form, and we'll get it on your Lorry experience record. If the QR code doesn't work for some reason, it'll just be lauriercs.typeform.com/CP164 midterm. It'll take you to the same link. So I'll leave this up for a couple minutes. Everybody who's in the Twitch chat right now, please sign up. And yeah. All right. So let's get started then. So this is our second review session of the year. If you guys missed our first review session, you can catch up on that in the video on the Twitch. But we will be going over some familiar concepts from that review session just so we're all on the same page for the midterm. Our next review session should be in 2 weeks' time. Just look out on the Instagram for that, but it's going to be on lists, stacks, and queues. These are going to be linked data structures that we're looking at. Then our last review session of the year is just going to be our final exam review session. So I'll pass it off to Mila, and we can get started right away with our review of last review session. I know, pretty meta, but what can you do?
Can you guys hear me? I hope you can. So let's get started with this review session by doing a little recap of the last one. So we're gonna take a quick do an overview of classes, data structures, and abstract data types. So let's take a look at classes. So here we have our class structures. So these are different categories of methods we can have within a class. So we can have our constructors, which initialize an instance of the class. So for example, this could be this is your initializer constructor. It's like the 2 underscores at the I, N, I, T, and then the 2 underscores. We got our accessors. So these return values of attributes. So, an example of this could be the get method. We've got mutators. So these modify values of attributes. So for example, this could be the set method. And then we've got iterators. So these sequentially iterate over the contents of the class. So let's go take a look at an example. So our class structure example. So we've got our class pets. We've got our variable here set to 0. And then here we have our constructor. So like I said before, this is, the way that you would write the method out. And then we've got our argument pets. We've got our keyword self. So that's the keyword that you're using for the attributes in the class in Python. And then that's set to the argument. We've got our accessors. So we've got get current, and then we've got mutator. So that's add, it's the same. So there's set, you can do add, delete, anything that really changes is a mutator. And then we've got our iterator that's going to be going through, the contents of the class. We've got the index self.n. And then when you do next, you're always going to be getting the next value, and you're returning that value. You're returning pet. So let's go over into data structures now. So we're gonna look at, what are data structures, how do we make them, and why do we use them? So let's do just a quick little recap. So what are data structures? Data structures are objects that efficiently store data to perform certain operations on them. And then this includes, obviously, you guys know of your stacks, your queues. You guys are going to learn about trees. And then there's a bunch more, obviously. One thing to keep in mind is that different problems require different methods of accessing data, or not necessarily require, but are probably more efficient. So for example, if the common stack problem is balancing brackets, so for this problem, it would make more sense to take advantage of the LIFO property of the stack instead of, for example, the queue, which follows the FIFO property. So yeah, essentially different problems can require different data structures to better efficiently solve them. So let's take a look at how do we make them. So Python provides some already kind of built-in implementations of certain data structures, and this includes lists, tuples, sets, and dictionaries. However, it doesn't have built-in ones, for example, for stacks or queues or trees, but we can go in and implement those ourselves using class definitions, and that's probably what you've already been doing so far in your assignments and your labs. So let's take a look at how do we use them. So kind of just like a recap of what I already just said. Yeah, so you leverage their features, their properties, and then when you do that, you take advantage of those. You can create more complex programs. And yeah, like different data structures can be more efficient for solving different types of problems. So yeah, make sure it's really important to understand the different properties of the various data structures and not to confuse between them. So let's take a look at stacks firstly. So what are stacks? So a stack is a data structure where the last piece of data inserted is the first to be removed. So it follows the LIFO principle, last in and first out. So yeah, here we have an example of these, warehouse pallets. And so the way that it would work is that they're constantly stacked on top of each other, right? And then some other maybe real world applications could also be like stacking plates, literally anything that can just be stacked, essentially. So let's take a look at the next slide. So we've got the conceptual kind of idea and how this works, essentially. So firstly, we've got the empty stack, nothing inside. When you push to the stack, you add to the bottom, right? So now we're pushing again. We're gonna stack on top. That's element 2. Then when you stack again, or push again, you've got up until the third element. And now when we do our pop, we remove from the top, right? So that's how it works. I think pretty simple to grasp. So let's take a look at how it would look in implementation in actual, in our Python language. We've got our constructor here, initialize constructor. We've got our accessor. Oh, no, not accessor. We've got our mutators here. We've got our push and our pop. And then we have our accessor here, peak. So the push, something important to note firstly is the push and pop. So the names, push and pop are names given to the methods in the stack. So we don't refer to it as insert or remove. So that's important to know because that's a property of the stack. So you definitely don't want to, definitely confuse things. And so second that I did want to say was also the way that it's getting pushed into it, right? So you're appending to the end. If you were to imagine it like a list, you're appending to the end. And when you pop, you also pop from the end, right? So if you were to make that like instead of a stack vertically, you'd make it horizontally, right? You're playing around with like the backside of it, the end, essentially. And so yeah, and then when you peak as well, you want to peak at the top of the stack. So you're going to peak at that -1 index, which is your last element. But yeah, okay, so that's kind of the main gist of what I want to cover in the implementation of a stack. So let's move on to queue. So let's go. what are queues? So a queue is a data structure where the data is stored and retrieved such that the first element is inserted and where the first element is inserted is the last to be removed. Yes, that is the FIFO principle, first in, first out. So let's take a look at how this would conceptually work. So we've got our on queue, we've got DQ. So on queue, we are adding to the rear of the queue. DQ, we are removing from the front of it, right? Now it's not just where the stack was only dealing kind of with that back, the ending, you're removing and adding to the back. The queue is add to the back, remove from the front. So let's take a look at how this would look in code. So we've got our constructors, our mutators, and our accessors. And so here we have on queue method. So we are appending to the back. Once again, it's the exact same as the stack, you're appending. And then we've got DQ where, so here, important to note is pop at 0 index. So we are popping from the front. It's not the same as the stack where you're popping from the back. So yeah, those are kind of the, and peak, that would be the next. Very important to note is that for a queue, you peak at the front of your list. That's right, you're using a list in Python. That's where your values are getting put. So you are peaking at the front of the list. Also, one more thing to note, definitely, so the names again, make sure that you aren't confusing between the different names, in a queue, you don't have push and pop. I'm pretty sure I use insert, remove for queue, but it doesn't really matter, like just use whatever your professor has given to you. So like when you guys implemented this in your assignment, whatever the method names were there, just know that those methods are for that data structure, just the way they're called. And yeah, so that's the implementation, kind of a recap of queue. And so let's take a look. Let's take a look at lists. So what are lists? So it's a data structure where data is organized as a collection of sequential elements, each consisting of a unique index of its position. So lists, just remember, linear fashion, basically. We all kind of know what lists are, so I won't waste too much time kind of going through that. But let's look at a visualization. So I guess you could look at this like a queue, maybe look at it like a stack in a way. But the gist of kind of, so not just, but like the main thing about lists is that you can access at index, right? So that's kind of their property, is that you can access an element at a particular index. So here, for example, if we wanted to access the element at index 2, we could do that in the list implementation. I believe you guys, it's definitely a lot longer than the other ones for stacks and queues. So you have a lot kind of more, I would say, flexibility. You can kind of go in and grab whatever data you want at a certain index or reassign data at a certain index. Whereas, for example, like a stack and a queue, you're not, that's not how the property works for those, right? You've got the FIFO and LIFO properties. So you have to kind of, those are your rules and we have to stick to them. So yeah, that's a list and how it would like conceptually work, which you guys are probably very familiar with. So let's move on to the code. So here, yeah, like I said, so get item. So you've got your index here, that's your argument. You can see like you have the index argument multiple times. And that's right, it gives you the opportunity to work with something at a piece of data at a particular index. So let's take a look. So here, for example, for append, right, you have self value. So append, naturally, for append, you're just adding to the back. But for example, if in this code we were to have insert, I believe your insert would look like you would have two arguments, right? You would have insert value and I, right? So you can insert at whatever index that you want, and you make the program so that it it makes sense whether you're inserting before or after a certain index, right? So that's kind of the main thing about lists, is that you get to play around with the indexes. For peak, works the exact same as a queue. You are peaking at the first element of the list, and so that's kind of the gist of stacks, well, classes, stacks, queues, and lists. I hope that clears any confusion you may have on them, but I'm gonna pass it back to Steven, and he's gonna walk you through the Big O theory.
All right, so before we get into Big O theory, like what is Big O and Big O notation, let's answer some of the questions that are in the Twitch chat right now. People are asking if there will be a recording of this after. Of course, our recordings will stay on Twitch for a while. I believe they're still posted as well. And an interesting question about deep copy. So if we were looking at the data structures that we were using before, so what deep copy does is it makes sure that it's kind of more of an advanced subject, but this is discussed within your lecture notes, so I'm kind of just passing it on to you. It's never tested or anything, but this is just what your professor says. So what deep copy is pretty much it creates a copy, obviously, of whatever it's being referenced to. So let's say, for example, we have two objects, student 1 and student 2. Let's call student 1 just student 1. So if we were to say student 2 equals student 1, and then we go on and change something within student 1, if we were to print out both of these, they would now be equal to the same thing. Because when we say something is equal to another thing, it's just referencing that within memory. But when we say deep copy, we're creating literally another instance of the object or whatever parameter we're pointing at. We're creating another instance of it. So this is just to make sure that whatever is being referenced to when we're doing peak is exactly what we want to be referenced. It will be pointing to a different part of the memory. Again, like I said, it's a pretty advanced subject. I'm not really explaining it all too well, but I promise this isn't going to be tested ever. But just remember that deep copy is just important to have if you're ever asked to implement like a stack or a queue for these peak for peaks for pretty much the accessors of the data structure. So just keep that in mind. All right, so let's move on to Big O theory and Big O notation. This is a very crucial part of computer science as a whole, and you're definitely going to run into this not only in this course but in courses to come, and definitely in the workplace later on, definitely in job interviews as well. So what is Big O notation? If it lets me go to the next slide. Hello. Okay. So what is Big O? Big O analysis is used to analyze the efficiency of a given algorithm. The lower the Big O notation is, the more efficient the algorithm is. So let's look here at this running time complexity in terms of Big O. So as we can see here, as the Big O starts to get bigger, so log of n would be the smallest of all of these Big O's. It's going to be the least. Sorry, I'm just reading the Twitch chat. So the first review session was streamed on Twitch as well, but it wasn't broadcasted, so not a lot of people joined. But I do believe Recursion is on the midterm. Correct me if I'm wrong. I'm not too sure if Big O is on the midterm, but it's definitely a very important part of the course. So we're just going to go over those two things as well today. So, okay, sorry, to the people in chat, I guess Recursion is not on the midterm. So it's just everything that we covered beforehand that's on the midterm, which is kind of odd. They're going slower this year, I guess, than previous years. But regardless, it's fine. We can just keep going through with this and yeah. All right. So as we can see here, as the n's get larger, so whatever the n is, it gets the rate of increase for the algorithm is a lot higher. So think, for example, if we have 1 million inputs, log n, or O of n, let's take because it's an easy example. O of n would be just 1 million. For example, it would just like go over it once per input n. So it would be 1 million calculations. But if we look here at O of n of c, for example, let's say c is to the power of 2. This would be 1 million squared computations. So obviously this is going to be a lot more computations for the computer to handle, and it's going to take up a lot more memory. So as we can see on this side here, O of 1 is our constant time. So these are operations like print, there are setters and getters. Usually these are always O of 1, they're constant time. Log of n is something like a binary search, which you'll encounter as well later on. I'm not sure if it's going to be in this course, but definitely later on within your computer science degree. O of n is something like a for loop. O n log of n, so involves nesting. We're going to look over that as well. And then all of these are kind of not really run into very often. Definitely not the factorial or the c to the power of n. These ones are rare to see, but the n to the power of c is run into quite often, and this is also due to loop nesting, which we'll look at now. All right, so common big O time complexities, like I was explaining before, let's just take a look at how they occur within code so you guys know how to spot them, and we can tell apart, or we can determine what the big O is of a certain algorithm. All right. So a constant time complexity, like I was saying, standard arithmetic, so c equals a plus b, this is always going to be constant time. Regardless how many times you do this, it's always just going to be one computation. It's pretty clear to see why that is. And so whenever we have anything of constant time, regardless of how many times we do it, it's always going to simplify down to O of 1. So even if we do this calculation 1,000,000 times, the computation isn't going to be if we have 1,000,000 inputs into this, it's still going to be O of 1 because each of them require constant time. Okay, so let's look at linear time. So for loop is the best example of linear time. We all know how for loops work. So we're going from one point to another point. So for this example, we're saying for I in list. So we're just going through every single element within the list. So the time complexity of this is we're always looking at every single element in the list once. So this would be based on the length of the list. So O of n, meaning O of the amount of inputs that are given. So this is why it's a linear time complexity. If the list has 1,000,000 elements, then O of 1,000,000 is pretty much what we're going to have, O of n. So as this keeps going, it's going to be like a linear path. So the more we put into it, it's not going to grow any bigger. It's just going to go at a linear rate. So this still isn't too bad in terms of efficiency of an algorithm. So let's look at something a little bit more complex. It's logarithmic time complexity. So we know how while loops work as well. We're given a conditional statement, and while it's true, we run the loop. So in this case, we have while I is greater than 0, and then I is going to be equal to I divided by 2. So when this happens, every single time we're cutting the amount of parameters that we have to go through by 2. So this reduces the time complexity down to log n. So while loops that prune the data, for example, are always going to have log n time complexity because they're not going to go over every single piece of data once. They can go over it a lot less amount of times, but log n is just the standard that we simplify it down to. So if you see a while loop that's cutting the data, it's always going to be O log n time complexity. But however, let's go back on that point because it's good. Not whenever you see a while loop is it going to be logarithmic time complexity, because while loops sometimes, if we're just saying while I is greater than 0, but we're just saying I plus equals 1, for example, this is still going to go through every single element while I minus equals 1, so because we're going down, it's still going to go through every single element in the parameters once, so that'll still be linear time complexity. So when we see a while loop, it doesn't automatically mean that it's logarithmic time complexity. We have to delve deeper within it to understand that it is logarithmic time complexity. So whenever it is cutting the value or not going through all of the values, then we know it's more likely going to be logarithmic time complexity. All right, so now let's look at exponential time complexity. So this happens when we have multiple for loops within like each other. So in this case, we have for I in list and then for j and I. So let's say, for example, we have our list is a 2D list. So obviously, this is still going to go through every single element within the list, but now our list is 2D. So we're going to have n by n elements that we have to go through. So it's pretty simple to see why this is going to be n squared time complexity. So there's a question in the chat. Will while always be the best? Again, it's dependent on the scenario or the situation that you're in. It depends on the situation that you're in because, again, a while loop can be just as not efficient as a for loop if it's still going through every single element in the list. But if it's cutting the values, then yes, it'll be more efficient. So another question in the chat, are brute force solutions always O of n by m? So that's a good question. Brute force solutions is pretty much a solution that looks through every single possibility. So the answer to your question, I know it's not very good of an answer, but again, it depends. So if the brute force solution to a certain problem makes you go through every single input once, then it'll only be O of n. But let's say a problem does require you to go through a square of problems, then yes, it'll be O of n times n. It's really dependent within on the scenario. And yes, this is going to be uploaded as a VOD on Twitch, so keep an eye out for that. All right, so the best way, obviously, to do things is to go over an example. So let's go over a quick example about how big O is kind of determined. So let's look at this function. This is a function you may or may not have seen before. I believe it might have been in one of your assignments. So it's an intersection. So we're taking a target. So the intersection that we're checking is, so our target is a set and we want to take one value. A set is obviously a list with only one of each element within it. Sorry. So pretty much all we want to do here is for value in self. So self is a list and we're checking if it's in both self and source, then we want to add it to the target. So whatever is in both these lists, we're just going to add to the target and we only want one of each. So our first thing is our target equals set. So all variable definitions are going to be constant. So if we say A is equal to 100, set isn't extremely relevant, no, but it just makes this calculation easier so we don't have to check whether or not it's in the list. But no, set is not extremely relevant, but it's just to prove a point that we want this to be only one of each value within it. So yeah, but again, set is not relevant to the big O time complexity. If we were to say target equals an empty list, it would be the same, it would still be constant. If you were to say target equals 100, if we wanted to, it'd still be the same, it'd still be constant time. So for value in source, or for value in self, sorry, we have to go through every single value in the for loop. So all for loops are linear, like we know, unless, of course, there is a break within it, and then the time complexity is kind of up in the air. But by definition, all for loops, or everything that goes through every value once, is going to be O of n time complexity. So this is a tricky one that I see a lot of students messing up on. I know I did when I was taking CP164, but it's this if statement here, if value in source. So what this does is it checks every single element within the source, and if it's value, then it stops, but then it keeps checking every single element in source. That's just how the if statement works. If that's how the in within the if statement works. So this as well, even though it seems like it would just be a constant thing because we're checking, it searches through every single value in source. So this as well is pretty much like a for loop in the sense that we are looking through every value within the source list. So this is if statement as well is a O of n time complexity. And then, like we said before, adding a value is always constant. So this, because we have nested O of n complexities, would become O of n squared time complexity at the end of the day. And so the way this exponential work is, let's say we had another for loop within this, so for value in self, and then for value in source, and then we have if value in source, let's say, but it's like 3 levels of nesting, then it would be O of n to the power of 3. And this algorithm is obviously worse than the O of n squared because we're going through values more than once and more than however many n squared is. So I hope this gives you guys a good understanding or of the basics of big O notation. But if you don't understand it, we'll definitely take some questions once we get through all of the material. But it's definitely a good thing to learn about because it's very important within the field of computer science. And yeah, that's all I have to say about Big O. So I'll pass it off to Noah and we can get started on recursion.
Hello. I hope you can all hear me. So we're gonna start covering recursion. So recursion, what it is, how does it work, and what are its applications? So what is recursion? So you see here, there's like a photo. This is recursion. It recurs. Recursion. It recurs, and it's like a sort of infinite-looking photo. Sorry, I want to make sure the slides are up ahead enough. Yeah. So there's like an infinite like looping thing here, recursion. It's sort of like the Borax box. Have you ever seen that? But it's when something is defined in terms of itself. So recursion at its most basic, means defining something in terms of itself. And recursive algorithms have 2 main parts, which are the base case where recursion does not take place, and then the recursive cases where the function is called on a different value than previously given. And so here there are a bunch of common use cases for recursion, which is when a function is defined in terms of itself, at least outside of the base case. And the common use cases are the following. So functions that need to call a previous result of the function as part of the current results definition. And one of the most well-known would be the Fibonacci sequence, which adds the last 2 numbers in the sequence to create the current number. So here we have a Python recursive algorithm for the Fibonacci sequence. So we have 2 base cases, n either being equal to 1 or n being equal to 2. N is the parameter for the function. So if this is the case, then the result is 1. Else, if n is not equal to 1 or 2, then the result is equal to the Fibonacci function of n minus 1 plus the Fibonacci function of n minus 2. But and we look back at the Fibonacci function, we see if we put n minus 1 as a parameter, then we'll continue shrinking down and down and down until we get to n being either equal to 2 or n being equal to 1. And we will have that with the n minus 1 case and the n minus 2 case that we put into the Fibonacci functions. And we return result every time that we find the result in the Fibonacci function, whether it's the base case or the recursive case, we're always returning that result value. But yeah, sorry, I'm seeing in the chat, it's saying my mic is not working well, but I could be wrong. I don't know. Maybe it's talking about someone else, but yeah, sorry. Here's another example of recursion that we're going to go over. So here, the example, we have a list of some names, and these names are Obi, Safe, and Robert, just 3 names of people. And then we have a function called phone call, which is here's a description of it. Imagine you want to have lunch with your friends, but each of you only has one of the other's number. Obi has Safe's number, and Safe only has Robert's number. Each has to call the next until so that they can relay the information backwards using recursion. So here's how you do it. If the list that's passed as a parameter is empty, then lunchtime is 1 p.m. else lunchtime equals phone call list starting from 1 after the first thing in the list. So that's what the 1 with a colon does. And how it works is, so first, when we pass this, let's say we pass the list of OB safe Robert, right? In the first time, it's going to repass the list back into the function, but this time it's only going to be passing safe and Robert. Then, because safe and Robert's not empty, it's going to pass it back in. It's going to put in Robert, and then it's going to get empty. It's going to be 1 p.m. and everyone is going to make sure that they know about the lunchtime through this recursive function. They can get the information to everyone. So if there are any questions, we can type them in chat, I think, and then after that we'll be doing a Kahoot. So I guess we'll give it back to Steven for that, and yeah.
Can you explain what you mean by why isn't it 0? Oh, why isn't it? Oh, I didn't... Bro, sorry, I didn't notice that. It was a face. My bad. But yeah, drop any questions? Or would you guys prefer we do the Kahoot first or take questions first? I'm up for whatever. And just the Kahoot first, okay. Like, because isn't it meant to start from the first item in the list? Oh, okay. So let me just... Oh, you're talking about this function. All right, okay. Let me explain it a little better, because I wrote this function and I kind of gave it to Noah without a better explanation, so kind of sent him out in the dark. Okay, so what I was trying to convey in this function is kind of the backtracking nature of recursion. So the way it works, we're going... the computations happen bottom up. So once we get to our base case, which is the very bottom, then we go up a level, up a level, up a level through our recursive cases. Or for the case of the Fibonacci sequence, for example, we start at the very bottom with the two, 1 and 2, and then we like branch up +1, +2, +1, +2, so on and so on until we get to the very top of it. So in this example, once we get to the end, this is pretty much like the bottom. So only Robert knows what time they want to meet at, and like Safe only has Robert's number, OB has Safe's number, and so on. They don't have each other's numbers. So the backtracking works. So when they get to the very bottom, sorry, I can't focus with the chat. Yeah, terrible example. All terrible spots, bro. Lizzie's, Osmos, and Mosey's all overrated, but it's O of N, obviously, because we're going through each one of the elements. Okay, regardless. So once we get here, we get to the end. When the list is empty, we get to the bottom, and then we go back. And so the function now has that 1 p.m. information to pass back up one level and further up one level until we get back to the user of the function, or to get back to each level in the function, like so that each level of the function knows what the return value is going to be. So the recursion has like that kind of backtracking kind of ideology to it. So that's what we were trying to explain with this function here. So just think of recursion as like a bottom-up kind of calculation of whatever you're implementing. All right, so like we talked about before, let's just do the Kahoot first, and then we can take any questions after. So if you guys want to qualify to win gift cards, make sure that you put like just the name of your Laurier email. So not like the @mylaurier.ca, just whatever is before that. Oh, I see. I was completely misunderstanding the question. Yes. Unknown Salib perfectly like described what we were saying. So the reason it's not 0 is because that indexing isn't what's it called? It's non-inclusive. So when we say 1 colon, then it takes everything starting at 1 going onwards. So if we were to say 0, like Unknown Salib said, it would just return the same exact list. It's like we were doing nothing. So that's why we do 1 colon. Oh, sorry. I don't even have the volume on for this. Oh yeah, bro. Return of the King, bro. Steven Goat is back. But they might not qualify for gift cards if they make the podium. So I really appreciate the name, but like, for your sake, I change it. Guys, there's 42 people in this Twitch chat. I want every single one of you in this Kahoot right now. It's like for your benefit. It's not even for me. Like, what do I get? A little ego boost. You guys get the chance to win, like, gift cards. So. Yo, I have no clue if these are bots or not, but... Yo, whoever said Moses is better than Laziz, it's like mid versus mid. The rewards are gift cards. I'll have to ask what they are, but I believe it's $25 to someplace. It's free money is what it is, but yeah. Guys, I'm gonna... Oh, somebody ordered. Okay, yeah. Thought they were still in. No, it's everybody who's it's first, second, or third. All three will get gift cards. So don't be too demotivated if you don't get all the questions right. I'm sure you can still place on the podium. Okay, we'll give another minute for the 11 or the 10 now that aren't in from the Twitch chat. All right, 10 more seconds to everybody that's not in. If you don't get in, you're missing out. Okay, 5, 4, 3, 2, 1. Okay, let's start. True or false, stacks follow the FIFO principle. Well done to the people that said false. So the people that said true, I think you're mistaking them with a queue. So a queue follows the FIFO principle, stacks follow the LIFO principle. So last in, first out. Whatever you put in most recently in a stack gets taken out first. So that is LIFO. And then whatever you put in least recently in a queue gets taken out first. So that is the FIFO that we were talking about. I mean, Holly, yeah, if you do get the podium and you want to give it to somebody else, that's I don't think we can be the middleman for that, but like, if you want, yeah, sure. Name 6, well done. Wow, it's not even anybody that can qualify. That's kind of... Wow, whoever's mood 2560, that's such a dope my Laurier idea. All right. What is the time complexity of this method? Holy shit. Okay, sorry, we might have not given enough time for this, but I guess this one's a shot in the dark. Well, whoever got that one right, hats off to you. But let's look over it so that we're not completely hopeless here. All right. So again, this is a union function. I believe this one is similar to the one in target in intersection. My bad. So it takes everything, but it takes everything from both of the self and the source. So we're saying if length of self is greater than 0, this is always going to be constant because it's just a length. It's just an attribute. So then we have a for loop, which is going to be O of n time complexity. And then same with this, if I not in target values, that's also going to be O of n time complexity. And then this append is just going to have constant time complexity. So this chunk is going to be O of n time complexity. So let's look over this one. This is pretty much the exact same, except we are comparing source 2 instead of self. So it's the exact same. This chunk is also O of n squared. So for the people that answered O of n to the power of 4, the reason why it isn't that is because there's no nesting within these two chunks of code. So it'll just be 2 times O of n. It will be 2 times n squared will be the time complexity, but we can just drop the 2. Because if you think about it, if we have a million parameters or a million inputs, for example, it'll be a million to the power of 2, which is going to be however big of a number is. If we multiply that number by 2, it's not really going to affect that much, like not as big as the n squared. So we're always taking the most relevant or the largest big O, just so we can simplify. We can see that we can compare methods and algorithms more efficiently. So that is why this is O of n squared, because there is no nesting, only nesting within each of these if statements. So, but whoever guessed O of 1, like constant time, it's just bad guess. Maybe get better at guessing, but that's the advice I can give you. Wow, the entire leaderboard changed off that one. Well done to those that are up there now. Let's dethrone these two people, though. Let's get people who can actually win on the podium. All right. So Python has built-in implementations of data structures such as... Yeah, Sully, we did make all of these in Replit. It's just kind of the easiest thing to get a common theme going. So yes, lists, sets, dictionaries, and tuples are data structures that are included within Python. Red is incorrect because stacks and queues aren't. Blue isn't correct because stacks aren't. And yellow is incorrect because queues aren't. These are native implementations. Like obviously these data structures you can implement by yourself, but Python in and of itself does not have built-in implementations for these. So well done. We got to get Moses out of here. Sorry if I'm rooting against you. That's kind of rude, but you can't win prizes anyway, so. So queues have a pop method, true or false? False. Well done. So the methods that we use for queues are the mutators of queues are going to be enqueue and dequeue. So that's just what they're called. So these are the ones that follow the LIFO property. Pop is what we use for stack, and this follows these follow the FIFO property for queues, and stack. The pop method follows the LIFO property that is used in stacks. So that's why queues don't have a pop method. Man, the more I pray on Mosey's downfall, the more they arise, man. Okay, so this one's multi-select. So stacks can be used to solve. Which of these? Yeah, so it was all of them that are correct. So converting infix to postfix is just like different ways of doing mathematics. So it's best doing it in a stack because we can kind of see which ones come in last, and then these are going to be first. So infix is like, I don't remember which one is which, but the one infix or postfix, one of them is like the normal way we do math, and then the other one is like there's 15 questions. I know we made this one tough, so to those who win, I salute you. But okay, so the operators come before the two like values. So like let's say we want to add 5 and 6 together, we'd say plus 5, 6. So infix is the normal one. Postfix would be the operators come after the value. Sorry, this is all like mixed up in my head. But so we say 5, 6, and then plus. So if you think about it, when we do LIFO, we'd like to know which were the ones, like which were the values that came in most recently to like that's why once the operator comes in, we'd like to know which are the two values that came before it, so that we can pop both of them out and then do whatever that operator is. So that's why we can evaluate postfix expressions with it, and then converting is like the same kind of principle. We're doing it the same way. Whenever we see an operator, we're taking out the two most recent things from the stack and then creating them into a string, for example, because we want it to be infix. And then like Mila said before, we can determine if an expression has balanced symbols or balanced brackets is the most, like this is an interview question that comes up all the time. It's just a pretty simple data structures question. So we can see, let's say we have a right bracket. We can check if the top of the stack, the most recent thing was a left bracket, then we can pop that out and that'll be balanced. But if it's not, then we can just return false because we know that that right bracket is closing a left bracket that isn't the same type of bracket, if you know what I'm saying. Like if we have square bracket and circular brackets, if we have a normal circular bracket, but the most recent thing to go into the stack was a square bracket, then we can just return false. So let's get a move on here because we're only a third of the way through. Yeah, let's go. Damn it, bro. Damn it. Yeah, I'll definitely take that into account, Saliba. I'll put more time on these Kahoot questions. I just didn't want to make it too long. What is a real-world application of a priority queue? So we haven't really discussed a priority queue as of yet, but just think of it as a queue, but the thing at the that has the most priority, or the thing that is most important gets taken out first. So well done. So waiting in the emergency room is the correct answer because obviously, let's say somebody comes in with a finger, like they cut their finger just like a little bit, they have a splinter or whatever it may be, and then somebody comes in after with a broken leg. We clearly want to treat the person with a broken leg first. So even though they came in after them, we still want to treat them first because they have higher priority. So the reason why all of the above isn't correct, it could be used, but they're just not real world applications. Waiting in line for the movie theater, you can't just cut in line because you're more important person, obviously. Like that just doesn't really happen. Just wait your turn. So that's just a normal queue. Placing boxes on top of each other is more an example of a stack, like we said. So whatever we put into the stack goes on top, and whatever we take off from the top. So it follows the last in, first out property. So let's move on. What is the correct linear search algorithm? All right, so the red one was correct. So let's look over this. I'm sorry if it's small, but I don't know if I can zoom in on this, but I'll read it out regardless. So the red one says, assign 0 to an index variable, typically I, that tracks which value in the list is currently being examined. Compare the value at index I to the key. If the index I has not reached the end of the list, and if the value at I matches the key, then stop looping and return I. If key has not been found, increment I, repeat until key has been found or I has reached the last index. If key is not in the list, return -1. So this seems like a pretty normal linear search algorithm to me. We go through everything in the list. If we find it, we can stop. That makes it more efficient, but we can keep going as well. So assign 0, I'm reading the blue one now if you guys can't see on the stream. Assign 0 to an index variable, typically I, that tracks which value in the list is currently being examined. Compare the value to the index at I. If the index I has not reached the end of the list, and if the value at I matches key, return I. If key has not been found, increment I, repeat until key has been found, or I has reached the last valid index. If the key is not in the list, then return -1. So the reason that these are different is if the index I has not reached the end of the list, and if the value at I matches key, return I. So this one, the blue one doesn't work because we don't stop looping. It's just going to keep going, which doesn't really make sense because the whole point of a linear search is we want to just return I. So yeah. Circular queue uses methods like append, pop, and insert. So false. A queue uses the enqueue and dequeue methods very similarly to a normal queue. So that's why a circular queue doesn't use the pop and insert methods. Okay, well, looks like a lot of people that are valid to win prizes are getting up there, so that's good to see. So true or false, recursion in every time it's implemented in an algorithm does not define a scenario for a base case. So yeah, a scenario for a base case always has to be provided because if not, we're just going to be recursing forever. It's not a very good thing. It's like having a while loop without ever getting to the end of it because we're not incrementing a value. So make sure whenever you're writing recursive functions that you start off with the base case. So which of the following are applications of lists? Yeah, so it is all of the above. Sort does not really matter in a list. It doesn't matter how the values are arranged. Either of them can be valid. There are sort functions that we can do on normal lists, and they're valid. List of foods is just fine because it's just a list of foods. But yeah, so it doesn't matter if a list is sorted or not sorted. A list can be used just fine. So priority queues must use stacks to define the properties of their elements. So yeah, this is false as well. So a priority queue mostly just uses a list to define its elements or define its properties. The stack is not really applicable here because we're doing two completely separate things. And yeah, well done to the people that selected false. So stack ADT has a push and pop method. So it's a given since we've already done the queue one. Yeah, well done. So it is true. Like we've said multiple times, stacks use push and pop as their methods. Their yeah. So the peak method for a queue, does it let you see the next element in the queue? Lets you see the value at the front of the queue. Value is not removed. Both A and B or none of the above. Yeah, so it is both A and B. It lets you see the value, the next element to leave the queue, which is also the value at the front of the queue because we're using the last in, first out method here, or ideology. So whatever is, or first in, first out. Sorry, see, I always get them mixed up as well, but you just gotta know you gotta understand what like the stack in the queue does. So queue pretty much whatever goes in first comes out last. Wait, first in, first out. Yeah, so we're going in order of their insertion. So whatever's at the top of the queue or the front of the queue is also going to be the next element that leaves the queue. So that's why both A and B are correct. No, man. Why is Mosey back on top? All right, come on, guys. I'm really betting on you guys to dethrone whoever this is. List ADT has a length attribute. Yeah, so the list ADT does have a length method. As you guys have probably seen, we can do if length of list. Yep, so pretty self-explanatory there. Come on, guys, last question. It's a home straight. This code is recursive, true or false? Aww. So yeah, obviously this is false. This is a pretty extreme example of what is and what isn't recursion. So obviously the question, obviously this code is not recursive because what we mean by recursive is it calls upon itself, which this doesn't. It's just a method that prints two things. So clearly this isn't recursive. To the people that answered true, maybe you didn't listen to what you're saying, but yeah, so this isn't recursive, by the way. It's just printing two things. So let's see who is on top. Wux6869, nice. Ruddo3496, and don't say who I think it is, bro. Please don't be who I think it is. Oh my god. Such a buzzkill. Okay, so I mean, there's no way for us to confirm who Mosey is. I hope I can get all of these people. I hope I can get whoever's in fourth, but bro, Like, the thing is, I don't know who it is. I'd assume it's the person who said the Mosey's question, but, like, I can't. Oh, yeah, okay, if anybody has a screenshot of them being Mosey, and they can send it to me, DM me at Steven Like Sandwiches right now in the next 30 seconds, I'll get you your gift card. But if not, then I'm gonna have to pick whoever's on fourth, and I hope I can do it here. Shh. Okay, back to podium. It's at Steven Like Sandwiches, by the way. All one word on Instagram. If you can DM me that picture, I swear we'll get you your gift card. But you have to also send me your Laurier email. Okay, whoever's Thak67, can you, like, just say the rest of your... Yeah, okay. Thank you. What's the rest of your Laurier email address? Just so we can email you and get you your prizes. If, obviously, Mosey does not respond, which... Alright, so, since our Kahoot is over, check your DM. No way. Okay, I don't know what the rules here are. It's somebody in LCS internal, so I don't know what the rules are around this, but I think that's fine. I'm not quite sure, but if it's not, then Krisht401, could you send your, just drop your the rest of your email address in the chat so we can get you your prize. If, like, I'm not sure how the prizes are gonna work, but we'll figure it all out, and the people that got on the podium rightfully will get on it. Okay, thank you. That's perfect. All right, so I guess we can open the floor up now for questions. Any questions? We'll do. If there are no questions, then we can end it here. I always have such a good time with you guys. We never want it to end, but, you know, we got places to be and things to do. But yeah. All right, I'll keep the floor open for like 2 minutes because there aren't. Hardest thing on the midterm? I'd say the multiple choice, I guess, but okay. The OC CP164 has the midterm on paper closed book. Is this the case for the in-person CP164? I'm assuming it is. I'm not sure if it's on paper for sure, but somebody in the chat could answer that for me. That would be great. Okay, well, you don't have multiple choice on the midterm. There you go. That's always the hardest thing for me. Okay, so they have online. It's not on paper. Oh, so it's open book. So there's beef between the two, huh? I don't get what the point of online courses is if you can't take the exam also online. Like, I swear that defeats the purpose. I don't know. Correct me if I'm wrong, guys, but like, you just like don't get. You're still paying full price for the course, right? Like. Yeah, that's correct. If you return I in a for loop, it stops the loop. Yeah, I know, it's ironic. Lightning FC does make up a good point. I think it says a lot about society as well. In-person class has it online. Online class has it on paper. That's a cruel world. Yeah, see, look, online course is more expensive. What is this shit? Sorry for swearing, but it's got me heated because I'm also taking an online course right now, and my exam's in person. I'm like, what? Yeah, I mean, we're not monetized anyways, but I mean, you guys can monetize this right now if anybody wants to to donate, but like I would recommend against it because I think it violates school policy. But like if you do it, I'm probably gonna have to refund you, but it'll be funny. So oh yeah, you can't donate. There you go. Oh yeah, we're not even like I forgot you have to be like a Twitch partner and all that. My bad. Yes, I'm not affiliated. Damn, I'm not valid. Not certified. Serious shit. Does anyone know if this is the case? I think that might be the case for that. Um, because it might be just like a course that you're auto registered in. Like, correct me if I'm wrong. I really am not sure because I don't know if it was the case for me when I did CP164. Um, but yeah, Mila, could you help answer this question for me? What was on your midterm and
Yeah,
what data
of
structure were
course.
you assigned to do? Do you remember? Because I
Yeah.
don't remember what was
Also
on
for
mine.
the other one, I think that is true. Like if you are in a Bachelor of Science in Computer Science, like you're not allowed to take the OC version. I've heard people say that before, but like yeah, I'm not really sure 100%. So that might be a lie. I don't know. But also for the midterm, yeah. So like mine, basically last year, like mine and Noah's, we didn't have there wasn't multiple choice. Like it was the same thing. Like you have the whole internet at your disposal and everything. And yeah, like you're gonna have to code a data structure and you're gonna have to code functions that use data structures. So that's why like I was emphasizing a lot, like know data structures and know like their properties and stuff, because you are gonna have to code one and you are gonna have to use them in different functions. And I'd say honestly, the hardest thing, at least for me, was it's a time crunch. Like I don't know if it is for you guys if they made it like that again, but for us it was like you had 50 minutes to like do all of this stuff, and like it's really like it just manage your time wisely, because the midterm is meant to be hard and like throw you off a lot, but the final is different. Like you get a lot more time for the final, but yeah yeah, so you're gonna have to be coding, so know your data structures well and the properties and stuff. Am I like am I like allowed to go like into I don't know how like
Yeah, I
in
think you can divulge information on previous like things.
am
If you
I
can, yeah, yeah, you can say the
okay?
data
Yeah.
structure for sure.
Oh, okay, yeah. So we did set. So no, that was kind of like we put it in here in like the little, the Kahoot, and it was even in the slides a bit. So like research what a set is, and I'd say like, you know, make sure you know how that works.
Ye-
And yeah, that's the one we had to do. So
Yeah, so kind of the formula about how they like create these like the data structure question for the midterm. They take like something that you guys have like it's always going to be an array based data structure. So it's going to be something like similar to a list, stack, queue, something like that. But like something that yeah, exactly. They never taught sets yet. Exactly. But it's something that you guys haven't learned. So they want you to apply your learning to just extend kind of. It's not like you're going to be creating will they do what they have done with dictionaries? I'm not sure, but yeah, so the way it usually works is like they take a pretty basic data structure that's not taught, but it's very similar to the other things that you do, but it has a few extra properties that they want you to code in to see if you understand how these attributes are like implemented. From Saliba, all the CP programming courses do they have the same assignment system? Like a few questions you solve, but it's not a project, or does it start becoming project based? Yeah, so yeah, it does kind of start becoming project based. It depends like which ones you do. Like I know CP363, when I took it, it had a lot of projects, but they've kind of made it into shorter things. There's some courses like CP, yeah, but usually they are kind of the same. It's a few questions, but they do get a bit longer. Like I know 264, the assignments were a bit longer. Yeah, like CP 213, there was one like large assignment at the end. I believe the VBA one, I think that's 212, right? That one has a large one. how much harder does comp sci get into the upper year? If someone has a lot of difficulty in CP164, do they have a chance of moving forward? In my opinion, it doesn't get that much harder. Maybe I'm like wrong in saying this, but Mila, you can correct me if I'm wrong. Maybe it does like it doesn't get too much harder, but I would definitely recommend that you do have a good understanding of CP164 because these concepts are extremely important going forward, especially for a course like CP264, which is data structures but within C, like the C language. Hardest courses you've done so far? I'd say CP264 is pretty hard. Algorithms is kind of hard. Like that's CP312. Yeah. What are some of the easy electives? I'd say CP212 is really easy. I've heard
I don't say CP212 is easy because they changed the instructor, so now it's actually gotten significantly.
Okay, CP212 I guess is not easy anymore.
But it is easy. It is an easy course. It's just Hyder is a little bit weird.
There's the one I know for sure that's easy is web development or whatever. It's CP368, I think. That one's easy, but like I think it's an upper year course, so maybe wait a bit on that. But if you're someone that takes 8 to 12 hours to solve a lab or assignment, that's when it will be hard. Yeah, I guess you could say that, yeah. But no, these labs are supposed to take you, or the assignments for sure, are supposed to take you a little while to do. I don't know if 8 to 12 hours, that seems a lot, but what are your thoughts on CP317? Let me look up that course code because I have a terrible memory and I don't even remember what that is. Oh, software engineering. Oh yeah, CP317 was really easy. That's a good course to take if you're looking for a really easy comp sci course. That's true. CP317 was really easy when I took it. And I'm pretty sure it's mandatory yeah, exactly. You have to take it, right? So, do you do projects? It's one project at the end. It's very simple. But it's more of like theory-based software engineering. So it's just like the principles, like the theory of it. You're not really applying it until the very end for like a pretty short project that you do in a group, and it should be like maybe a 10-hour time commitment per person. It's like not too big of a deal. Yes, no. David Brown is a great prof, but in CP317, if you get it with him, I've heard that's bad. But yeah, I can't state if it is or is not downhill from here. I think that violates school policy, but I hope you can gauge from my reaction from like what that means. But is Fatima a good prof? Yeah, I'd say she's.
I beg to differ on that one.
Fatima is a good prof. I had her for algorithms. If you're talking about like Dr. Fatima, which I'm assuming you are, like not her first name, but yeah, she's a good prof. Is there a lot of upper years who's dropping out of the program, switching? I don't think so. Not that I know of. Like I'm double degree, and so is Mila. So a lot of people who drop our program just like go to business. But I don't really know too many just like straight comp sci kids. But so I couldn't really tell you. But I don't think so.
Definitely like don't stress difficulty though. Like once you guys like I think 164 is definitely gonna be like a learning curve for you guys. Like for some of you maybe, like if you're not, you've never seen some of this stuff before in your life, but like to be honest, just do the assignments on your own. Like even if you're tempted to look at other people's code and stuff, like do it on your own because like that's gonna help you the most. Like you want to build the logic and like that way of thinking, and like Steven said, like it actually doesn't, like yes, sort of courses, sure, like in terms of content they could be more difficult, but like at the end of the day, like as long as you have that logic and right way of thinking, like you can, like you'll tackle any other problem that you come across. Like code at the end of the day, like syntax you can learn C, give yourself like a week and something, as long as you have the logic there, like you'll be fine. And that's kind of what it is going forward mostly. I'd say like sure you'll have like a math course here or there, you know, you learn new things, but like, yeah, like I wouldn't stress so hard on like the difficulty of the courses. Like, trust me, like once you get over that learning curve and like you build that logic, like you'll be fine
Yeah,
in any other
yeah,
course.
I definitely agree with that. Yeah. Yeah, I think you are done with math after MA 103. Like CP,
214, that's what I'm taking right now.
yeah,
Like that's
CP.
like proofs, but yeah, that's like math. Like that's what I call math, but like yeah, like it's not really coding, so I call it math. Like
What was
it
my
is math.
favorite elective? Like again, like I said, I'm in double degree, so I don't get many electives. I think I get like two my entire program, and I just fast tracked instead of taking electives. So yeah. How many hours do you guys put in per day studying? Right now, I'm on co-op, so zero. Yeah.
I would say like I don't know, maybe like five. Oh,
How is it co-op? Oh, co-op's great, man. Is it worth applying for? Yeah, absolutely. Unless you have a really like strong confidence in yourself that like you can get a job elsewhere. Yeah, I definitely apply for it. And like I'm in a CS co-op right now, but my first co-op was a BBA co-op. But yeah, it's definitely worth applying for. If you don't like the program after the first time around, like you already have the job experience from the first time around, you can just drop it. But do you have any chance of getting into co-op? Yeah, you definitely do. I think the admission average, like don't do the best. I don't know what standard you're holding yourself to, but I think the admission average for co-op is like a 9.5 or something. Can you tell us where you're working right now? Yeah, I'm working at Ford right now. I'm doing software development. Yeah, it's pretty fun. But yeah. How does co-op work in Laurier? I think it works similarly to most other schools. Yeah, there's hella CS students this year. So many more than like when I first came into the program. So co-op works very similarly. So if you're not in a co-op program, you have to apply to get into the co-op program. Yeah, you have to apply to get into the co-op program, and then once you're in the co-op program, there are like rounds of applications. There's like first round, which is like where a lot of people try to get their jobs. That's usually like first 2 3 weeks of school. Yeah, and then like you do that, you apply, and then whoever selects you for an interview, you have to go do that interview, and then after that, you can get ranked. So then you rank the employers that you interviewed with, they rank you. If you get a match, then you can take the job, or you have to take the job. That's just how it works. And then if you don't get a match, then you move on to the second round. And then if you don't get a match there, then you go to continuous round. And then, yeah, so how related is the co-op work compared to what you have learned in the program so far? Is it easy? Would you say like my co-op work easy? If that's what you're asking, yes. A lot of co-op work is like bitch work, for lack of a better word. They just give you stuff that they don't really want to do like themselves. Like if you get a good company, they'll like actually get you like working with stuff that's impactful. But especially with big companies, like I'm working at Ford, which is a huge company. Yeah, it's just kind of it's pretty easy stuff. But yeah, it's definitely applicable. Like the stuff you learn most in co-op, especially for tech, is just like learning how not the business side of it works, but like the planning and really like the software, like the engineering part of like software. It's not really the logic. Like like you're supposed to know all of that stuff before. It's kind of a prerequisite. So are there any advantage to having a higher grade when you apply for co-op? What do you mean by that? Like applying for jobs in co-op or applying for co-op itself? Because co-op itself, I'm pretty sure yes. But I don't know how it's like when I didn't have to apply for co-op, but I believe people who did it before me, it's just kind of a threshold, and then they base it upon the interview that you do afterwards. So my typical work duties right now are so we have these things at Ford called SWOD files, which are kind of like just huge Excel sheets with a bunch of part numbers. And I'm just like creating a tool to help automize like the creation and updating of it. So yeah, like pretty simple stuff, but it's definitely good. They're gonna mark you on 4 things: grade you, your actual interview, extracurriculars, and job experience. Yeah. Yeah, I'd assume like getting into co-op is pretty similar to getting a job. I don't think it's as like cutthroat, but yeah. I'm assuming they're gonna accept a lot more students to co-op this year. I don't think there's like a like strict line. I think they take everybody who's applicable, unless I'm completely mistaken in that assumption. I don't think there's a hard cutoff for the amount of people that they take. So so I saw a question above as well about MA 122. It's kind of off topic, but I liked MA 122. I've heard a lot of people say it was their least favorite course, and like a lot of people dropped because of it. But I honestly enjoyed it, and the thing with MA 122 is that it's like linear algebra is pretty important for a lot of stuff that you do in comp sci. Like especially if you want to work in like data science or anything like that, like knowing those matrix like operations is very important. So yeah, I think it's a very valuable course. So how did I fast track my courses? Yeah, so the way I fast tracked it is I did take my first semester summer. I didn't have any co-ops, so I took kind of I took 3 courses that summer, kind of arbitrary number. But then from there, anytime I had an elective or like free space, instead of taking something that was like an elective, I would just take something that was like just a required comp sci course. So I'm 1 class away from finishing my comp sci degree. I just have to take ethics. Actually, I'm 2 classes away. Sorry, but I have to take ethics and then principles of comp sci, and then I'm finished. And I still have most of my business degree left, so I'm not looking forward to that. Yeah, and the thing is, with a lot of the electives that you take in comp sci, I feel like the more interesting ones are the ones that are like senior level, and they require a lot of prerequisites. Not a lot of prerequisites, but prerequisites that you get like later on. Like most of them require 264, 213, or something like that. So that's why I decided to just like fast track the courses that I already had the prerequisites satisfied for. And like these electives that I'm talking about are obviously like AI, machine learning, like stuff like that, right? So yeah. All right, so we're kind of coming up on our end time. CP213 hard. Uh, I mean, I guess not really, but no, I wouldn't say it's hard, honestly. I think it's a good course. Like if you've ever programmed in Java before, which I think if you've taken comp sci in high school, you probably have. Like I know most schools did Java, at least my school did. Then it's pretty simple. It's just like kind of getting around like Java, but the stuff that you do in it is not very hard. It's all stuff that you've kind of done. I haven't taken web dev yet, but I am planning to do it in the summer because I have school in the summer. I've heard it's really easy, and it's like a free project that you can put on your resume after as well. So yeah. But yeah, we're kind of coming up on our 8:30 end time. There's a class called web development. It's CP368 if you're interested. Is it an exclusion? I'm really not sure. For me, it's not. I don't think. But correct me if I'm wrong. What's an exclusion with? Just with comp sci? Oh, CP202. I don't even know what CP202 is. I haven't taken that class. Oh, website design. Oh, I see. Yeah, I think CP202 is okay, okay, okay. I see. So CP202 is web design. That's a different class. CP368 is the one that I'm talking about, which is I don't think it's called web dev. It's called something like, let me look it up, sorry. Oh shit, so maybe it's not 368. Maybe it's like 468? I'm really not sure now. No, that's AI. What the hell? Uh, 476. Oh yeah, there it is. Okay, 476 is the class I was talking about. It's called Internet Computing. From the grapevine, I've heard it's pretty easy. I haven't taken it yet, but yeah, planning on it. All right, so I think we're gonna have to wrap it up here. We don't want to really go over our allotted time. But yeah, thank you all for joining us tonight. I had a great time. Mila's kind of preoccupied right now, but I'm sure she had a great time as well. I don't know if Noah's still here, but he did as well. But yeah, I'll catch you guys in the next one. Bye. Have a good night. Have a good rest of your reading week of what's left of it. Be safe. I'm sure you guys will do great on this, and I'm sure all of you guys will get into co-op, so like don't stress. But yeah, thank you guys. And for those of you guys that won the Kahoot, I'm not sure how many of you guys are still in, but we will be in contact with you. So have a good night, everyone.
Bye, guys.